Hello and welcome to this explainer. You know, if you've ever stared at a world map and wondered, why does the Earth actually look like this? Well, you're in the right place. We're about to peel back the surface and look at the magnificent, completely invisible machinery that drives everything. I mean, we're talking about the engine that builds mountains, carves oceans, and triggers earthquakes. So here's our roadmap for today. First, we'll unpack the continental drift mystery. Then, we'll decode seafloor spreading, look at the unified tectonic theory, and explore Earth's dynamic boundaries. Finally, we'll wrap up with hotspots and the tolls and something called the ocean life cycle. Let's get right into it. Section 1. The Continental Drift Mystery. It's actually kind of crazy how quickly our understanding of this huge geological mystery evolved. I mean, it all happened over just about half a century. Back in 1912, a meteorologist named Alfred Wegener looked at a map, noticed the continents fit together like puzzle pieces, and proposed this wild idea called continental drift. Fast forward to the 1960s, and Harry Hess outlines seafloor spreading. Then boom, just a few years later in 1965, Ch02 Wilson puts it all together into the unified theory of plate tectonics. This timeline perfectly tracks a massive paradigm shift in how we view the Earth. So let's talk about Wegener. He suggested that about 200 million years ago, there was this massive supercontinent called Pangaea. And as proof? It's honestly undeniable. Look at the fossil range of the Mesosaurus. These 250-million-year-old fossils are found in South America and Africa, and nowhere else. Obviously, there is zero chance this small freshwater reptile swam all the way across the Atlantic Ocean. So this matching fossil data is essentially a smoking gun, proving these landmasses used to be seamlessly fused together. But, and this is a big but, science needs a how. You need a mechanism. Wegener tried to argue that the Earth's rotation and tidal forces were what broke Pangaea apart. The scientific community, however, flat out rejected that. Why? Because tidal forces are literally physically incapable of pushing massive rock continents through the solid ocean floor. So without a plausible engine to drive it, his theory was just shelved.
Which brings us to Section 2.
Decoding seafloor spreading.
To find that missing engine, we've got to fast forward to the years following World War II. During these massive, unprecedented ocean surveys, scientists stumbled upon a giant chain of underwater mountains, a mid-ocean ridge running 65,000 kilometers right through the middle of the world's ocean basins. So in the 1960s, Harry Hess proposed seafloor spreading to explain this. The idea is that heated magma, fueled by the Earth's natural radioactivity, rises up, setting up these massive convection cells. The magma breaks through at the ridges, cools down, and forms brand new crust. Because of this, the crust's age literally gets older the further you move away from the ridge. It goes from 0 days old at the center to millions of years old at the edges. And if you want absolute, undisputed proof of seafloor spreading, it's all about magnetic striping. See, as that basaltic magma rises and solidifies, it actually magnetizes based on whatever the Earth's magnetic field is doing at that time. And since the Earth's magnetic poles periodically flip-flop, the seafloor records those reversals. What you end up with is this perfect mirror image barcode of normal and reversed magnetic striping on either side of the ridge. It's brilliant. It proves beyond any doubt that new crust is being generated in the middle and symmetrically pushed outward.
All right, Section 3. The unified tectonic theory.
So by the mid-60s, we had proof that continents moved and proof that the seafloor was spreading. Enter systems analyst Ch02 Wilson in 1965. He took continental drift and seafloor spreading and basically fused them into one overarching operating system, plate tectonics. He figured out that the Earth's rigid outer shell, the lithosphere, isn't just one giant solid eggshell. It's a highly dynamic matrix of puzzle pieces, or plates, each about 80 to 100 kilometers thick. We've got major ones like the Pacific and African plates, and minor ones like the Cocos plate. Driven by those deep convection cells we just talked about, these plates are constantly moving, mostly independently, at a rate of roughly 2 to 10 centimeters every single year. Basically, about as fast as your fingernails grow. Section 4. Earth's dynamic boundaries. Now, if you've got giant puzzle pieces moving around a sphere, they're obviously going to crash into each other, scrape past one another, or pull apart. They interact in three main ways. First, you have divergent boundaries, where plates pull apart, creating rift valleys and mid-ocean ridges. Second are convergent boundaries, where plates crash together, generating deep ocean trenches, heavy earthquake zones, and massive mountains. And third, transform boundaries, where plates just grind side by side, creating some really intense fault lines. Each type of movement results in radically different, totally distinct topography.
Let's check out a live terrestrial example of a divergent boundary. Look at the East Africa Rift Valley. The lithosphere right here is actively splitting apart, forced open by a shallow heat source bubbling underneath. It's a massive linear depression that is literally ripping the African continent in two. Given enough time, and we're talking millions of years, this exact rift is going to drop below sea level, flood, and potentially form an entirely new ocean basin, kind of like the Red Sea just to the north. On the flip side, let's look at what happens at a convergent boundary, specifically subduction. Here, a super dense oceanic plate is colliding with a lighter, less dense continental plate. Because the oceanic plate is heavier, it sinks, or subducts, straight down into the mantle. As it gets dragged down, the insane heat and pressure melts the plate. That newly formed molten rock then rises back up to the surface and violently vents as a highly volatile volcanic mountain range. The towering Andes Mountains down in South America, that is a textbook, real-world result of this exact subduction process.
Moving on to Section 5, Hotspots and Atolls. Okay, let's step away from the plate edges for a second and look at localized thermal anomalies, hotspots right in the middle of plates, and the really cool biological structures that track them. This builds on a brilliant hypothesis Charles Darwin actually came up with while sailing on the Beagle. Darwin noticed coral reefs only grow in shallow, sunlit waters, right? So step 1, a new volcanic island forms from a hotspot, and a fringing reef grows around its shallow edges. Step 2, as the incredibly heavy volcanic island slowly subsides or sinks into the crust, the living coral has to grow straight up, about 3 to 15 millimeters a year, just to stay in the sunlight. This creates a barrier reef and a lagoon. Finally, step 3. The heavy volcanic rock sinks completely below the ocean's surface, leaving nothing behind but a beautiful circular ring of living coral called an atoll. It is the ultimate tracking system where biology perfectly maps geology.
And finally, Section 6, the ocean life cycle.
Now that we've decoded the micromechanisms, let's zoom all the way out. The Wilson cycle, named after our guy John Tuza Wilson, tracks the complete lifespan of an ocean basin over hundreds of millions of years. It starts at the embryonic stage, like the rift valleys pulling apart in East Africa. Then it opens into a juvenile narrow sea, like the Red Sea, and keeps spreading into a mature, massive ocean basin with passive margins, think the Atlantic. But eventually, the cycle flips. Subduction kicks in at the edges, which is the declining stage. This is what's happening to the shrinking Pacific Ocean right now. As the continents close in, you get a terminal narrow sea, like the Mediterranean. And finally, the ocean closes completely in the suturing stage. The continents smash together and push up massive young mountain belts, just like the Himalayas. So oceans are literally born, they live out a lifespan, and then they die.
Which brings us to the end of our explainer. We've seen how continental drift, seafloor spreading, and plate tectonics serve as the tireless, hidden engines beneath our feet. So I want to leave you with this to think about. If oceans are constantly being born and destroyed in this endless Wilson cycle, and tectonic plates are shifting literally as you're watching this, what is the Earth's map going to look like in another 200 million years? The ground you are standing on right now is just a temporary arrangement. Keep exploring, and thanks so much for joining me.